Hey everyone, welcome back to my Calculus 1 series. In this lesson, we'll be going over the essential functions that are needed for calculus. So to start off, first we'll be going over the exponential function. The formula, or the way it's written, is as f of x equals b to the x. This is a more general formula where x is the variable like we see in every function, and then b is a base. That value changes from whatever your exponential function looks like. So essentially what a exponential function is that it is the base times the base times the base, and we do this x times. So if you remember, this is the definition of a power. When we say something like, okay, x squared, well, that means it's just x times x 2 times. But an exponential function will take this common base of, let's say as an example, b is 2, then 2 to the x. This will take 2 and multiply it x times. So if we go through the transformations of this function, they don't really change much, and they basically just stay the same as they would for almost any function. So plotting something like f of x is equal to b to the power of x plus c would look like something like this, where this right here, this asymptote, is c, and this point right here is going to be c plus 1. If you look at the original function, the exponential function, the base function b to the x, it will always pass through this point of 0, 1. And if we raise the c value, like if we add a constant to it, this new point will become c plus 1. And likewise, in a regular exponential function right here, there is a horizontal asymptote right here, and the asymptote is along the y equals 0 line. But if we add a constant to it, this c, we basically raise that asymptote up by c units. And likewise, if we were to plot something like f of x equals b to the power of x minus c, we would just be moving this asymptote downwards, and the point would still be here. Now for stretches, they basically stay the same. The graph just stretches out like this, still goes through this point. And then if we would like to apply a transformation to the x-coordinate, we can do that by doing something like this, b equals cx. And as we saw in the other video, basically the graph will just get compressed, but it'll still go through this point. And finally, as we saw for reflections, it'll be the same thing. So minus b to the x will look something like this, where this is minus 1, and then if we were to plot f of x equals b to the minus x, all that's going to do is going to change the way the function goes. So now it'll go this way. There are some important edge cases to note, and that is if we have this function and b equals 1, then we're going to have this horizontal line right here where this point always stays. It's always going to be 0, 1. But we're going to have this horizontal line because no matter what x value we put in for the power, 1 to the power of anything always remains 1. So we're going to get this horizontal line. Another interesting point worth mentioning is if we have the same function, b to the x, and x is greater than 0, however, it is less than 1. If it is within this range right here, then the function will it'll look as if it was like this, and we multiplied the x by a negative. It'll basically just switch directions to here. I haven't dealt with these too much in my mathematical career, so I don't think you will be as well. The majority of the time you just deal with a b that is greater than 1. Now an important note worth mentioning is I'm going to write the domain ranges for the function b to the x, but the domain for it would just be that x belongs to all real numbers. And if we go back and look at our original sketch right here of the base function b to the power of x, we can see that the function will hit all x values. However, if we look at the range, it is restricted because of this asymptote, along the line y equals 0. We won't be able to go below it, so the range will be restricted to values that are greater than 0. So the domain is x belongs to all real numbers, but the range for the function would be that y belongs to all real numbers such that y is greater than 0. Another important function to talk about, it falls kind of in the category of these two, but that is if we have a base that's equal to the number e. If I remember correctly, number e equals to 2.72 something something something. And essentially why this number is important is because it has tremendous applications to like natural like growth rates, specifically when you start dealing with things like population modeling or like the half-life of something. So the value, the base e, becomes really, really important. And we call this the e to the x function, the natural exponential function. Now moving on to some of the laws, if we have something like b to the power of x plus y, we can break this down into b to the x times b to the y. Likewise with subtraction, if this is going to be multiplication, then the subtraction one will be division. The next exponential law deals with a power of x to the power of y, and we can simplify this by just saying that it is b to the power of xy. The last exponential law will have to deal with the distribution of a power, and so if we have these two values a, b inside the brackets and they're both getting raised to the exponent x, we can simplify this and say that it will be a to the x times b to the x. So I probably went over that pretty quickly, but there is nothing really new for exponential functions. There's nothing really you haven't seen from exponential functions to the other functions that we covered. The transformations stay the same. Everything stays the same apart from these like little exponential laws that you might want to note down or something. The next big point that we'll be talking about though is inverse functions, and these are also really important because from them is derived the logarithm, which we will cover next. But to get into the essence of inverse functions, essentially all it is just reversing the x and y coordinates. So if we think about this little statement right here, just reversing the x and y coordinates, graphically this would mean that we take whatever the x coordinate is and we swap it with the y coordinate. So if we take a look at this point right here, this by the way is just the function that we were just talking about, b to the x, any b. And if we look at this point, the point is 0, 1. So if we were to change this, we would get a new point, 1, 0, and it would be somewhere here. And then if we were to do this for a series of points, all that would happen is that you would get a graph like this. So graphically, what an inverse function does is it will take your original function, which is this one right here, and it will basically flip it over this line, the y equals x line. Because if you think about it, that's what we're doing. We're changing the y and the x coordinates. So all we're doing is basically flipping along this line. This method works for any function. However, it does get pretty hard to draw some of the more complex function. But that's all you're doing. You just take your graph and you flip it across this y equals x line. A couple of other ways to explain what the inverse of a function does is if we go back and take a look at the drawing that I made when I was first explaining what a function was. Let's say that this is our domain right here, and we have a bunch of, let's say, just variables a, b, c, and d. And then we had our range, right, which had like f of a in here, and then it had like f of b in here, it had f of c, and f of d in here. And what this function f did was it took the element of a domain and it mapped it to an element of the codomain or range. And if we think about an inverse, what it does is the complete opposite. So if you notice in this graph, I drew the arrows pointing this way, but the inverse noted like this, -1. The inverse will take elements of the range or codomain and it will map them back to the original. Take f of d and it will map it back to d. It will take f of c, map it back to c, f of b, map it back to b, and then f of a and map it back to a. And that's what this inverse function right here will do. So I did mention the notation for it, but just to go over it concretely, the inverse of a function is written as f minus 1. So it's not to the power of -1, it's just the notation of the inverse. And so the relationship between f of x, just the original function, and the inverse is as such. If we were to take the y-coordinate that our function would give us and plug it into our inverse, we would be given x. So that is the relationship between two functions. And we'll go over an example of this. Two important features of a function that are kind of useful for finding inverses are the definitions of surjectivity and injectivity. I won't be formally defining them, but if you do end up taking a discrete math course or something, you will probably go over what it means to be surjective and what it means to be injective. But I will kind of dumb it down for just this video. And essentially what we're looking for when we talk about those two is that a function is one-to-one. In a previous video, we talked about the notion of being a function and that you would only want to map one x to exactly one y coordinate. So that is half the definition of being able to have an inverse. In order to have an inverse, you would actually need to pass both the vertical line test, meaning every x could only map to one y, and you would also need to pass the horizontal line test, meaning that every y could only map to a single x. So if we look at this example right here, this function will pass all the vertical line tests. However, the horizontal line test, I can almost take any horizontal line here and it will intersect the graph at exactly 2 points, which is not good. This means that this function right here does not have an inverse. However, if we were to look at something like here, this function will pass all the tests. It will pass all the vertical line tests as well as all the horizontal line tests. So a function like this would be able to have a inverse. Now, a more formal definition would be that f of x1 would not equal to f of x2 whenever x1 is not equal to x2. So what this definition basically means is that if we take any two x coordinates and they are different, their y value should also be different. So this is a more formal definition, but essentially you would be able to determine whether a function has an inverse or it doesn't based on if it passes the horizontal and vertical line test. So now working with actual algebraic inverses, let's take an example function called f of x, and we'll say that it is x cubed plus 2. To find this inverse, I know that the shape of this graph looks something like this, so I know it will have an inverse. I don't need to double check that, but generally you would want to check to make sure that it does have an inverse. But for this purpose, I know that it does. So to find the inverse of this function, what we're going to do is, like we said, interchange the x and the y. So originally the function is written as this. So now x is going to take the spot of y and y is going to take the spot of x. And for all purposes, we could leave the function like this. Like this is valid. However, a lot of the time you would want to isolate for y. So we're going to go ahead and do that. So now that we've completed isolating for y, we can see that this is the inverse of the function that we had. And we can observe another relationship with inverses is that these two statements will always hold. So if we take the inverse of our original function, we will get back with x. And likewise, if we plug in the inverse function to our original function, we will be left with x. We can kind of go on to test this. It won't be a formal proof or anything, but just know that both of these hold. But we can just go on to test this with our example. So we have f of x, it's this, and we have f minus 1 of x, which is this right here. So let's test this formula right here. So we're going to take f of minus 1, which is the cube root of x minus 2, and into the value of x, we are going to plug in the value of f of x. So we're going to plug in x cubed plus 2 minus 2. And if we go to simplify this, we can see that we are going to get these two terms cancel. We're going to get x cubed in here, the cube root of that, which is just equal to x. So that holds, and we can go on to test this one too. We're going to take f of x, and into every x we're going to plug in the inverse. So we're going to plug in the cube root of x minus 2 cubed, and then add 2. So that this power and the cube root would cancel, so we would be left with x minus 2 plus 2, and the minus 2 and the plus 2 will cancel out, so we'll be left with x. So that one holds too. And if we do these two kind of checks, these are usually a pretty good indicator that we have found the inverse of the function. But the purpose of that was just to show you that these two relationships hold, and they do become kind of useful sometimes when we're dealing with like exponential functions and logarithmic functions. So logarithmic functions, essentially logarithmic functions are the inverses of exponential functions. So if we look at the relationship between them, we can notice that the log base b y equals x, and this is the same as saying log b, b to the x is y. Now, since they're inverses, using some of the properties that we talked about, plugging in to our function right here, the inverse, this will get us back to x, and likewise, if we take this, the inverse of it, and we plug in our original function, which is the logarithmic function, we will still get back to x. So that would look like b to the power of log bx, and that equals to x. So like I mentioned in the exponential section of this video, we do have that important number called e. It actually has its own logarithm. So the logarithm with a base e is written as ln. And essentially this right here, the ln function, is the inverse of e to the x. So these two are inverses. And with this ln of x, we can observe a couple of things. One of them being that the ln of e is 1. This is a very, very useful formula right here. Another one would be that ln e to the power of x is equal to x. This one right here will make a little bit more sense once we go over the laws of logarithms. It's actually fairly simple, but essentially you could see why it would equal to x. It's because we have this original function of ln base e, and then we have its inverse being plugged into it, so it will get us back to x. And then we also have the opposite of it, which is we'll take the inverse function, e to the x, and we'll plug in the original function, and this will get us back to x. So these are just some useful formulas to know. They usually help a lot when you're trying to simplify things. So moving on to logarithmic laws, the first one we will start off with is the multiplication of two variables. And we can simplify this by saying that it is equal to log of b, and then inside the brackets it's x, but we can also add to that the log of by. So if we ever see something written like this, we can instantly simplify it to this version right here. Likewise, if we have the division of two things in here, it'll be equal to the log base b of the first one, the first variable like on top right here, minus the logarithm base b of the second variable. Now this one is really, really useful for simplifying stuff, and like I mentioned over here, it's going to make a lot more sense once we learn this law, but essentially what it is that if we have a logarithm with a base b and we have an x value to the power of r, we can kind of drop this r and bring it in front of our logarithm, so it can simplify to r log bx. So yeah, that's essentially it for logarithms. They're just the inverse of an exponential function, and the reason I included them here was because we talked about exponential functions, we talked about inverses, and it would just make sense to include this logarithm, which is a combination of both. It's the inverse of an exponential. So lastly, we will cover inverse trigonometric functions. You won't be dealing with them much in Calculus 1. You get more into them in Calculus 2, but still then I'd say you don't really need to fully grasp them. You just need to grasp the concept of an inverse and what you can do with it. So starting off, the inverse of sine of x, this is given in the form of arc sine x. It can also be written in terms of the inverse notation. Then for cosine, we have a similar thing. It's called arc cos of x, and it can be written in the similar inverse notation. And lastly, we have tan of x, which is, as you can guess, it's arctan of x. And it can be written as tan minus 1 of x. Now, obviously, there are more than just these three. I mentioned them because these are the main three, like sine, cosine, tangent, are the main three functions that you're going to be dealing with. But again, you don't really need to know too much about their inverse. You just need to more or less know about the properties of an inverse. And I'm just going to quickly pop up a graph and show you what these functions look like, so you can kind of have an idea about them. So these are what the functions look like. Arc sine goes through this point of 0, 0, and it also has this point of 1 and pi over 2 and minus 1 and pi over 2. And the reason we kind of truncate it is because if we don't, then it will go back here and it will no longer be a function. So it's just this little one piece. Likewise with cosine, or cosine I should say, it does have definite points right here and here. And again, we do truncate it because otherwise it would go back up and then it would no longer be considered a function. Arctan, on the other hand, is the only continuous one, and it kind of resembles tan itself. Tan usually goes like this. So as you can see, there are similarities, and it doesn't actually truncate anywhere. It just keeps going on till infinity, but it does stay between these bounds of pi over 2 and minus pi over 2, which makes sense because the original tan function has asymptotes here and here. So that is it for the essential functions video. I hope you guys enjoyed it. If this video has helped you out in any way, please leave a like and comment what you liked about it. If you are new to this channel, please like, comment, and subscribe. I would greatly appreciate it. And yeah, see you guys in the next video.